Good afternoon. Okay. We've been talking the last time about weak acids and weak acid titration with a strong base. And we've also been talking about buffers, and we're going to talk more about buffers and weak acids and some specific weak acids. And by now, you should be able to determine or to describe such a titration curve of a weak acid with a strong base. And you have certain points. You have the pH here of a weak acid, and if you compare this with the pH of a strong acid, it will be different if you have the same concentration of weak or strong acid, and you know now why. You have here the buffer region. We will talk about this. Then you have the equivalence point. At the equivalence point, you have all the weak acid converted to HVO. You have titrated, so the weak acid dissociates to HVO plus and AC minus, and you're titrating away that HVO plus with OH minus. So you're pulling out the HVO plus out of the equilibrium. With this, you have Le Chatelier's principle at work. So you're pushing more to the right side until you have all the HA converted to your AC minus, and you have then just water and AC minus. And if you would have a strong acid, that would be the equivalence point, okay? And that would be pH 7. But you have a weak acid, so now you have converted everything. If you, let's say you started out with a 0.1 molar weak acid, you have converted everything to AC minus. With this titration at AC minus, that reacts with the water. And this will determine your equivalence point, and it reacts, it makes more, goes back to undissociated acid and OH minus. And that OH minus tells you that equivalence point for a weak acid compared to a strong acid, that equivalence point will have a higher pH because you have this OH floating in your solution, okay? So you can do an ice problem with this. You say, my initial concentration of AC minus, that's when it's completely dissociated through your titration, is 0.1 molar. So if I make undissociated HAC and OH minus, I take 0.1 minus X, I call this X and this X, and this is now a base here. So I get a base constant. I look up the base constant for this conjugate base of the weak acid, look up the base constant, and I say, okay, X squared divided by 0.1 minus X equals, in this case, it's acetic acid, that base constant. You have to look it up. You need to know that base constant. And then you say, because this is such a small equilibrium constant, the equilibrium will be very much on this side here. And with this, I can say, that X that is dissociating is relatively small compared to the 0.1, and I can sort of neglect it, all right? And with this, you have then point X squared divided by 0.1. You bring the 0.1 over. 0.1 times 5.68 times 10 to the minus 10 is 5.68 times 10 to the minus 11. You multiply the 0.1 in there. Now you take the square root of this, because you have the square, you get 7.5 times 10 to the minus 6. What is X now? X is what? X is your OH minus concentration, okay? So that's the POH. You take a logarithm of this and multiply it with minus 1, then I have the POH. What would that be? That would be 5.12. 5.12, and if you take the logarithm of this, 5.12, you can calculate it. We did it the other day, I think. 5.12, and so POH plus pH for a conjugate acid-base pair is always 14 and 25 degrees. And with this, now you have your POH is 5.12. 14 minus 5.12 gives you the pH, and this will be 8.88. So the pH, the equivalent point of a weak acid with a strong base titration, will be higher. In pH will not be pH 7, but will be a basic pH. And vice versa, if you have a weak base, a weak base with a strong acid, it will be lower than 7. So you should be able to calculate something like this point, and this point, of also not only a weak acid, as I have done this here, but if I would be you, I would try a weak base, okay, and describe what the pHs at these individual points are. And I have given you a question at the end. I had asked you this question. We had compared the titration of a strong base, and you could answer that very well. But we did then the titration of a weak base, a weak acid with a strong base. That's our weak acid. That's the strong base, K plus and OH minus. So we titrate this with OH minus. And so what I do, this is my initial titration curve in yellow here. Okay, you have the initial pH, and you have your buffer region, and you have the equivalence point, and then you have these, what happens past the equivalence point. If these are these yellow lines, they're all the same. You dilute this by 10. What happens to that titration curve if you titrate it again? So you put 10 times more water in there, all right? And will it be A, B, or C? So think about it, and I just explained some of the things to you again, so maybe you can get an answer for this. You can discuss it. We had already the last time we had this as a question, and you sort of quietly answered it because many of you just went home. Or some of you. The first question you have to ask yourself, how does the pH change if you dilute it at the beginning, before you start titrating? Would it be a whole pH unit higher, or would it not be a whole pH unit higher? I said this earlier, okay? The second thing is, would be the equivalence point the same? Would the buffer region change? These are the questions you need to ask yourself. Yeah, we're getting there. Okay, let me see if I have something here in this thing. I'm looking for, not for this here, no. I come to it in a minute, okay. So, I agree with the C's. And so, first of all, we have our equivalent, our initial pH without adding any OH minus. Will that be going up by 1 unit, so the concentration will be diluted by a factor of 10? Will the concentration go down by 1 unit of HVO plus? No, it will not. Because you have HAC plus H2O gives HVO plus AC minus, okay? And so now we have all this water there, so we're pushing the equilibrium towards the HVO plus on the right side, and with this your pH will be not 1 unit different. So this is this one, this could be, that's not it, that must be it, okay? You also have seen if we take a buffer, and I showed you the last time, we diluted the buffer by 10. Okay, it did not change the pH at all, so the buffer region should not change. This would not change. This would be wrong then, okay? So the buffer region doesn't change. Would be the equivalence point, would the equivalence point change? You have the same amount of HA in there, and so you have adjusted a different concentration, but the equivalence point is not the concentration, it's the actual number of the pH, where you have the actual number of moles of HVO plus, or not moles, molecules of HVO plus neutralized with OH minus, okay? And that number does not change because you didn't change the amount of HAC, of the amount of weak acid. The concentration changed, but not the amount, okay? And with this, that would be this here. And now you're having 10 times more water in there, but you put 0.1 molar sodium hydroxide in there, So that means the 0.1 molar sodium hydroxide will be diluted to 0.01 molar sodium hydroxide. Okay, and 0.01 molar sodium hydroxide has a 1 whole pH unit lower, and this would be this here. That would be my new curve. This is lower here, that's the same, and this is not a factor of 1 higher, okay? A factor of 10 higher, I'm sorry. All right, there it is, smaller than 1 pH unit, moles of HAC unchanged, equivalence points unchanged, buffer region unchanged. Actually, yeah, this is moles, that's not moles per liter. This here is moles, not moles per liter, okay? Unchanged, and the buffer region is also unchanged, and here you just have the solution. Okay, we're going to talk today about polyprotic acid. So an acid has a proton that it can get off, that the base takes away. And the strong acid gives all its protons away, and the weak acid doesn't, okay? And so that means you have an acidic proton. We call this in slang, and especially with proteins and so on, we call this an acidic proton. So that proton can go off, all right? And so in the case of polyprotic acids, you have more than one acidic proton. So, for example, if we have, but I want to explain something to you before. Let's talk a little bit more about the buffer range, that you understand the proton off, proton on mechanism. Okay, and this, you will need this for your MCAT, because there will be a question about amino acids, what the charge of them is at a certain pH, and how the charge changes. So in order to set this up, I'm going to start where we began. Okay, again, so you have your weak acid, forms the conjugate base, and the H3O plus with water. Okay, so now you know this Henderson-Hasselbalch equation. That's the pKa. The pH is the pKa of that acid here, plus the log of the form that is the conjugate base divided by the acid, okay? So this is the Henderson-Hasselbalch equation. So what does it mean? So I have plotted here again for you, that's the pH, and this is the titration as you add OHs from here. You add OHs. So if you add OHs, what you do, you're taking this here with OH, you neutralize it and make water. That's all there is. And so you go along here, but there's buffering going on, and you see that there is a half equivalence point. And this is just the buffer region. I have to expand it tremendously. That's why there's a little bit of a slope here, but this whole thing is not this is about 1 unit here, okay? So we have 2 points now, or 2 cases. And if you have the half equivalence point, that means at half equivalence point, the concentration of this and the concentration of this is equal. So if they are equal, so that's the log of 1. This is the concentration, this concentration is equal, so this is the log of 1 and this is 0. At this half equivalence point, that means the pH is the pKa. This is this here, all right? Now, if you look at this form here, you have more acid form and less of the conjugate base form. That means this here is smaller than 1, the quotient, okay? And this means the acid form predominates, and if you have something that is smaller than 1 and you take the logarithm of this, what will the value be? Will be a negative number. So with this, the pKa minus 1 will be this here, okay? For example, if this is 10 times more than this here, if this is 1 to 10 here, for example, that will be minus 1, so this is the pKa minus 1. Now, let me ask you the following question. You look at this equilibrium, and you see, if I'm at pKa minus 2, the equilibrium you would go with me, the equilibrium is completely off the side here, is that right? Yeah. So that would be, let's say the pKa is here. What is the pKa? I can't remember what the pKa is. So if I go to a pH lower than the pKa, let's say 2 orders of magnitude, 2 units lower, would the proton be on or off? The proton is this proton. If it's off, it's this. If it's on, it's this. Would the proton be on or off? On, exactly. Even 1 unit, it's mostly on, okay? Now if I go here, 1 unit above, or 2 units above, is the proton on or off? Off, exactly. That's very good that you're getting this. So this is this side. That's the base form predominates. This here is the AC minus, is higher concentration than HAC, so that's larger than 1. You take a logarithm of larger than 1. If a number that is larger than 1, you get a positive number. And with this, you have then the pKa plus 1, if this would be 10 times more than this here, okay? So that means, that shows you if you're above the pKa in pH, then the proton is what? Off, exactly. So this is very, very important for amino acids, which will be discussing today. And so now let's come to polyprotic acids. That has polyprotic means many protons. Yeah? They can give many protons, more than 1 proton essentially. Poly means many, okay? And so thymol blue is an indicator. It has, as the name says, it must be blue somewhere. It has 2 protons and then this organic group, which is a pi electron system, and it absorbs light and has color because of it. And so this would be the polyprotic acid. It's a polyprotic acid. So we pull off the first proton with water. We put it in water and pull off the proton. Okay, it makes H3O, it makes HTY minus. That's the conjugate. That's the acid. That's its conjugate base. Okay, and that's now H3O plus. Okay, you got this? So you can write a Ka for this, and because we have more than 1 proton, we say Ka1. Ka1, and you can also make a pKa for this here. The pKa is 2 for this, and that would be here at the half equivalence point. What point is that the pKa? What pH would be the half equivalence point? Where I have 50% of this and 50% of this. What pH is that? Hey, half equivalence point. 2, okay? That's this point right here. That's pH 2 here, because you have 50% of this and 50% of that, okay? Now, this has a color. It has this pi electron system, and it absorbs light and has color, visible light. But this one, now you change the electronic system, so it's a different molecule, and it absorbs light differently, so it changes the color. So this is very handy by doing titrations. You can use this as an indicator. Now, we have this one here, the H-thymol minus, and this is still an acid because it has an acidic proton, and you react this reacts with water, and it gives that proton to the water. The water acts as a base, and this becomes, it's the acid, that's the conjugate base, and this is H3O, is the acid to that base here, okay? So, of course, you can have an equilibrium constant for this, and this would be Ka2, is the concentration of this times the concentration of this divided by the concentration of this. So that is pKa 8.8. What at this pH here, what would be the pH? We have 50% of this and 50% of that. What would be the pH? 8.8, exactly, okay? And so it has a different color at different pHs. It starts out with red. So if it's acidic, that's the pKa is 2, so pH 2 is red. If you are around pH 2, it's red. And as you increase your pH, it gets sort of greenish yellow essentially, that's probably 7 here, something about. And then it goes up into blue if you go into the basic region. And what would be that pH again? That pH would be 8.88, exactly. So you have an indicator which has a really wide range that it can cover. And that's what it is. So this indicates red in the acidic region and blue in the basic region, okay? Because of that pH. Yes? That is true, yeah. You have to use up the purple. But as you see, that pKa is 2. So the question was, do I have to use up all the purple before it starts, then that yellow can go into blue? You see, there's 6.8 orders of magnitude difference. So if you are here, let's say you add pH of 5. what predominates? Is the proton off or on? At pH of 5. The proton is off. So you're far away, you're all on this side, and it's all yellow. You still have to go to pH 8.8 to have 50-50. So there is that will be all converted. You see, just like this here, it goes from red, then it's mixed a little bit, and then it's purely yellow for a long time, then it gets mixed with blue a little bit, and it becomes totally blue. Okay? So why don't we do that experiment? And let's see if we can get some pleasing colors. So I have here, all of them have water in there, just like this. And you remember it was yellow on the screen, and about pH 7, that's water. And so this is all water. Of course, here I'm going to put sodium hydroxide in there, and here put HCl, strong acid and strong base. Let's start with the strong base. And so what should be the color be if I put sodium hydroxide in there? That should be blue, yeah? Okay. I'm a chemist after all, okay. So I put sodium hydroxide in here, and this became blue. So we are now at the form of the base, and we have all the protons off now, okay? Now, we're going to do something not so nice. We're going to put some acid in here. Oh, what a lousy color that is. What a terrible color. See, it's red. Now all the protons are on. That's on the bottom. But I don't like the color at all. So we want blue and gold, actually. Let's change it quickly. All right, very quickly. Okay, there you go. All right, so that's blue and gold. Go Bears. All right. All right. All right, so that was our demonstration, and you understand now how this indicator works. Of course, with an indicator, you are titrating a weak acid with a strong base. That's already, you're without an indicator. But now you put an indicator in there, and this indicator is also a weak acid. So that's why you only put one little drop in there. Otherwise, it would totally mess up your titration. If you put a lot of indicator in there, then suddenly you're titrating two weak acids with each other, with a strong base. And that's why you did the titration. Remember, you probably hopefully only used one drop of that indicator. Is that correct? Good. All right, you did it right then. And so polyprotic acids, this is the carbonic acid, H2CO3, that has two acidic protons that it can split off. H3PO4, phosphoric acid, has three acidic protons. It goes, the first proton goes off, it makes H2PO4 minus. The second proton goes off, makes HPO4 2 minus. And the third proton goes off, makes PO4 3 minus. So you have three acidity constants. And here you have two, and here you have two. This is sulfuric acid, and this is a weak acid, even if it burns holes into your pens, but it's a weak acid. And so the trend is usually, if you look at this here, that's for example 3, the Ka of the first one, the Ka, is much larger than the Ka of the second step and the Ka of the third step. That means the pKa is smaller than the second and the third step. Okay? That's just a repetition what Ka and pKa means. So I was sloppy, I left the water out of here. So now we have carbonic acid, H2CO3, and water gives HCO3 minus and HVO plus, and the water I didn't put it in, I was sloppy, all right? So it's not really balanced, but you know what the drill is of this here. And the pKa is 6.37. So I have now a solution of this here at a pH of 2. Is the proton on or off? On or off? pH of 2. What's with the proton? Is it on or off? pH of 2. Who says off? That's wrong. The proton is on. When is the proton off? pH of 7 or 8, the proton is off. You have to be above the pKa for this to be on this side, okay? And so now that's the first step. We have the first equilibrium. And then the second equilibrium is this here. That carbonic acid, that bicarbonate is called, HCO3 minus, reacts with water to form CO3 2 minus and HVO plus. This one is 10 to the minus 10.25, the constant. That pKa is 10.25. So if I'm at pH 2, is the proton off or on or completely on? Are there any protons dissociated at pH 2? Anybody? They're on, exactly, they're on. So I got the finger down, the thumb down, it says Nichi go. No, that person meant that it's on, okay, not off. All right, so because this one only happens when if I go between, so to go to here, I have to go like pH 9 or 8, something like this, then I'm here. And if I'm pH 11 or 12, I'm here completely, yeah? So, but if I'm here on this pH 9 and 8 and 7, so I'm going more and more here, and I'm here then, and now I go further, I go below pH of 6.37, I say pH 2, I only have this here. I don't have this, and I don't have this, and I don't have this. And this, of course, is the same here. So pH 2, I only have this because I have to get to the pKa, to the pH of the pKa, to have 50-50 off, okay? 50 on, 50 off, 50% on and off. And so what would be the ratio of CO3 2 minus and HCO3 minus at pH of 10.25? What would be the ratio? 50-50, okay? Would be 1. Of course, you remember, pH equals pKa plus log of the conjugate base divided by the acid, okay? And so at this pKa, I have this here and this here in equals concentration. The log would be then 1. It's because that's equal concentration. The log of 1 is cancelled. The log of 1 is 0. But this would be pKa. So 50-50. That's the half equivalence point, all right? So this is how a titration curve looks, for example. This is the first pKa. What would the pH be here? What's the pH here? 6.37. And the second pKa, what would be the pH be here? 10.25. Now let's go. I go to pH 14. What would be the predominant species? This here, or this here? pH 14. Totally on the side here. You're far above the pKa, totally deprotonated. Now go to pH of -1. Now let's not make it so difficult. pH 0, okay? pH 0. What would be the predominant form? No, only form, essentially. H2CO3, exactly. So now, see.